Welcome to today's explainer. If you've ever felt like math is just this rigid, boring set of rules you're forced to memorize, well, get ready to see it in a completely different light. Today, we are going to use the playful magic of algebra to become actual math detectives. We're talking cracking codes, busting myths, and solving riddles using the hidden structures of numbers. So let's get right into it. All right, let's jump right in with a quick puzzle. I want you to pick any 4 consecutive numbers. Literally any 4. Let's go with 3, 4, 5, and 6 just to keep it simple. Now, put plus or minus signs between them in absolutely any combination you want and calculate what you get. Take a quick second and think about how many different ways you could arrange those signs. Do you think the results are going to be totally random, or is there a hidden pattern waiting to be found? So think about the different paths you could take with those numbers. There are actually 8 different branching paths of positive and negative combinations for 3, 4, 5, and 6. You could add them all up and get 18, you could subtract them all to get -12, or you could do a mix, right? Like 3 plus 4 minus 5 plus 6 gives you 8, or 3 minus 4 plus 5 minus 6 leaves you with -2. At first glance, it looks like a completely wild spread of positive numbers, negative numbers, and even 0. But here is the crazy part. Look closely at all those results. Whether your answer was 18, -4, or 0, the absolutely crucial point here is that the result balances out to be perfectly even every single time. And it doesn't matter if you pick 3, 4, 5, and 6, or say 85, 86, 87, and 88, the total sum and the differences of any 4 consecutive numbers will always produce an even outcome, no matter how you arrange the plus and minus signs. The math just naturally balances itself. So let's look at why that happens in part 1, the laws of parity. Parity is really just a fancy mathematical word for odd and even. And to solve master cases, a detective needs a reliable toolkit. Memorize these simple rules, like how 2 odds mysteriously combine to create an even, or how an odd and an even will always, without fail, give you an odd. Once you internalize this basic rulebook, you don't actually have to do the heavy lifting of calculating massive numbers anymore. You can logically deduce the outcome of almost any equation just by looking at the types of numbers involved. Now, let's level this up and bring in some variables. Think of these letters as our algebraic suspects in a lineup. We're going to test these expressions to see which ones are guaranteed to be even, no matter what whole number you plug into the letters. And the best part? We don't need to test infinity. We just need our trusty parity toolkit. What's super interesting here is looking at an expression like 2a plus 2b. Because any integer multiplied by 2 is definitely even, we know for a fact that both 2a and 2b are even numbers. And what does our rulebook say? An even plus an even is always even, so 2a plus 2b is guaranteed to be even every single time. But that other one, 3g plus 5h, well, that one is a bit of a trickster. Let's interrogate this trickster a bit. If we plug in 1 for both g and h, both terms become odd. 3 times 1 is 3, 5 times 1 is 5. Add them up, you get 8, a nice, clean, even number. But wait. If we plug in an odd number for g, like 1, and an even number for h, like 2, things shift. 3 times 1 is 3, which is odd. 5 times 2 is 10, which is even. An odd plus an even gives us 13, which is odd, proving it is definitely not always even. Just by testing the parity rules, we solve the case. All right, moving right along to part 2, testing divisibility myths. With our new parity tools nice and sharp, let's use our logic to bust some common math myths. You know how people love spotting patterns, right? Well, sometimes our brains jump to conclusions that just aren't mathematically sound. Our first myth claims the sum of 2 evens is always a multiple of 3. And honestly, you can easily find examples where this seems to work perfectly. 8 plus 10 is 18, which is a multiple of 3. 14 plus 16 is 30, also a multiple of 3. But is that a hard algebraic rule? Let's test this with the absolute simplest numbers possible. Sure, 2 plus 4 equals 6, which works perfectly. But 2 plus 6 equals 8, which totally shatters the claim. 8 is absolutely not a multiple of 3. This is a great reminder of why we can't just take a few coincidences and call them a mathematical law. A rule has to work every single time, 0 exceptions. Okay, let's test another one. The claim here is, if a number rejects division by 18, does it automatically reject division by 9? It kind of sounds logical, right? 9 is literally half of 18, so maybe they share the exact same rejection rules. If a number like 40 isn't divisible by 18, it's true that it's also not divisible by 9. But can we find an exception? Well, actually, scratch that. A number like 27 completely breaks this myth.
27 isn't cleanly divisible by 18. It leaves a remainder. But it is a perfect multiple of 9. So the rule is only sometimes true, which means, mathematically speaking, it's busted. You always have to test the boundaries of a claim.
Which brings us to our final act, part 3, the master case, the pebble riddle. Okay, detectives, it is time for our grand finale. We're going to combine everything we know about parity, algebra, and remainders to solve a wonderfully mysterious poem. Listen closely to this. I hold some pebbles, not too many. When I group them in threes, one stays with me. Try pairing them up, it simply won't do. A stubborn, odd pebble remains in my view. Group them by 5, yet one's still around. But grouping by 7, perfection is found. More than 100 would be far too bold. Can you tell me the number of pebbles I hold? Basically, we need to find a mystery number under 100 that leaves a remainder of 1 when grouped by 3 or 5, but is perfectly divisible by 7.
So let's break these clues down systematically. First, the poem says pairing leaves a stubborn, odd pebble. That's a massive clue. Our parity laws tell us right away our final answer must be an odd number. Next, grouping by 3 and 5 with a remainder of 1 points us strictly toward multiples of 3 times 5, which is 15. So our mystery number has to be a multiple of 15 plus that one remaining pebble.
Because the poem specifically tells us the total is under 100, our lineup of suspects based on that 15 plus 1 rule is delightfully short. We just list out the multiples of 15 and add 1. We get 16, 31, 46, 61, 76, and 91. Our culprit is definitively somewhere in this list. Now we just need to apply our final filters to close the case. Applying our parity rules from earlier, we know the answer has to be odd, right? So we cross out all the even numbers. 16, 46, and 76 are out of here. That leaves us with just 31, 61, and 91. The final clue in the poem was that grouping by 7, perfection is found, meaning no remainders. So we test which of these remaining 3 is perfectly divisible by 7. Is it 31? Nope. Is it 61? No way.
Boom, there it is. 91 divided by 7 is exactly 13. The perfect solution to the master case is exactly 91 pebbles. We took a whimsical poem and cracked it wide open just by applying structure, parity laws, and some simple algebraic logic. The absolute most crucial takeaway here is that math is not just rote memorization or endlessly crunching massive numbers on a calculator. It is an incredibly powerful detective toolkit for decoding the hidden structures of the world around us. By understanding basic rules, you can predict outcomes, bust myths, and solve complex riddles. It really makes you wonder, doesn't it? Now that you have this toolkit, what other everyday mysteries will you decode next? Thanks so much for joining me on this explainer, and hey, keep your curiosity sharp.